Talking about radical reactions, we're saying that this is very useful to functionalize alkanes. But now the steps that actually, the first propagation step that we saw was the hydrogen abstraction. Say that I have a halide like that. So I am removing a hydrogen, and here is your homolytic cleavage, and you're forming this radical. Now, all the hydrogens are not identical in a molecule, so we're going to learn that we have hydrogens of different types in a molecule. Let's say that I have something like this, and here you have, say, this is a CH3. So here, if you extract the hydrogen at the end just by following that process, you will be making a primary radical. Now, if you extract one hydrogen from this position, now you would make something else. And that is a secondary radical. And it is, notice that the carbon where the lone electron is attached now, is terminal. It has another CH2. Now, this carbon here is attached to two carbon atoms. The secondary. Finally, we can remove here, remember that here you have one hydrogen, is not pictured in the line structure, but you can remove it, and now you will be forming the following radical, which is tertiary. So no, they are not equivalent. So in general, what we're going to say in alkyl radicals is that tertiary radicals are more stable than secondary, and those more than primary. And this in relation, the relationship with bond dissociation energy is that the more stable the radical, the lower the bond dissociation energy. In other words, these are easier to break. The bond here to extract this hydrogen, let me draw it. This one is easier to break than the secondary. The secondary was here. Here we have two, obviously. And here I'm going to draw the three primary hydrogens, see? And by the way, this position is identical to that. Point is that they're not all the same, and the weaker of the three bonds, considering the primary hydrogen, the secondary, and the tertiary, is the one that leads to the more stable radicals. So this is the weakest, then the secondary, then the primary. That will be important when we are predicting products. And also we have a couple more things that we need to mention here, which is a couple more, say, types of hydrogens. So if we have a structure such as that, and we extract one hydrogen at the allylic position, I'm going to draw the three. So say now that you have this radical, and you extract one hydrogen here, notice the fishhook arrow, and then the other electron stay here. Now you have a structure which is an allylic radical. This structure is stabilized by resonance, and resonance arrows are different when you do cations or anions, for example, than they are from radicals. And I'm going to draw it here. Let me see. I'm just going to keep that order. So we're going to, what we're saying is that all the hydrogens in a molecule are not equivalent, and we need to pay attention to that because we're going to be using that to predict products. So here is the order or how stable it is. So tertiary are more stable, and bond dissociation energy go the other way. So in general, so the more stable this is the weakest bond. So weakest, in other words, smaller bond dissociation energy. To that side, stronger bond. I'm going to draw the arrow the other way. So stronger bond to break. Now, considering the allyl radical, to see how the resonance structure explain why that will be more, even more stable than tertiary. So here we are, the structure of the radical. This time, remember that we need to use always the fish hook arrow. So we're going to move one electron on the pi bond and the other from here, and then the other to that end. And the resonance structure will look like this. You're making another pi bond, and this is that. So this is your resonance. Notice that we had used 3 arrows. So we use more arrows when we're doing resonance with the radicals. Another example of stable radical is, ooh, that's a terrible drawing. So I'm gonna say that I have toluene here. Now this position is called benzylic. And what happened is, in a step like that, we do the hydrogen abstraction, you will create this radical. This radical is also stabilized by resin. So we can have one pi electron from here and one pi electron here, and then the other pi electron staying over here. And now we will have a resonance structure. Notice that I did 3 arrows. I'm gonna have double bond here, double bond, double bond. That's one of the resonance structures. And you can continue doing that. You can move that and one of the pi electrons, and then the other pi electron, I'm gonna draw it over here. So you can have several resonance structures and one more, but I don't have a room to draw them all. But here you will have a double bond here, and there. And we have one more, and you can draw it. So this one electron with one of the pi bond, and then this is going to stay over there. Now the other structure, we have the lonely electron in there. So this is a resonance for benzylic. Point is now, having said this, the more stable of all the radicals that we are forming here is the benzylic, followed by the allylic, and then tertiary, primary, secondary. So overall, say that regarding stability, we're going to say benzylic is more stable than allylic, that more than tertiary, and this is more than secondary, and obviously more than primary. And this is the smallest bond dissociation energy, easier to break, easier to form, and that's important when we are now studying how to predict products in radical reactions.